Okay, so in question 19 of this E1 review, we've got a situation where we've got another very similar question to 18 in terms of the type of question, in terms of a lot of unknown variables and sort of making comparisons between two scenarios. So sphere A of radius r is placed in a container of fluid density rho. It's known that 75% of the sphere A is submerged. So maybe it might be helpful to draw a couple of pictures here. So we've got a container. We've got 75% of. Do my best to draw. It's a sphere where we've got 75% of the density. We've gone below the submerged, basically below the surface. So this is the situation for A, and this is the density of rho, the fluid. Now in B, sorry I didn't give myself much room. I'm going to draw a larger container. We've got a much larger sphere. It's placed in a container of fluid density 2p and 55%. So it's a much larger sphere, and about half of it is below the surface. A little more than half. Drawing something like this. This is 55%. This is B, but this fluid is different, and this has a density of twice the density of the fluid that A is in. Okay, so we're looking for the ratio of masses. So again, it's a flotation type question. So again, making our key condition for flotation is that the buoyant force is the same magnitude as the weight. So F buoyant for situation A is going to be rho, which is just the rho of this fluid, times G times the volume displaced, equals the weight of A, which is the mass of A times G. So we'll go ahead and cancel out those G's. And the volume displaced in this particular case is going to be linked to the volume of block A, which we know is 75% of it. So rho 0.75 times the volume of A is equal to the mass of A. And the volume of A is the volume of sphere. Volume of A sphere, to be specific. So 0.75 4 towards pi, and it's r cubed. It has just a single r. So that's our quantity. Oh, sorry, mix matching my upper lowercase here for A's. Okay, so the mass of A is rho of the fluid, and 3/4 times 3/4 of the volume, which in the volume of the sphere, but in radius of r is 4 pi r cubed. Now if we carry out a similar process for block B, hopefully I'll give myself some room here. So I'm going to skip the steps. It's going to be rho 2 times rho G times the volume displaced is mass of B, so I'll skip down to this step for B. So it'll be 2 times rho. This time we have 55% of the volume, so 0.55. We still have the 4 pi, and we have 4 towards pi, but it's 3 r. So the volume of B would be 9 r cubed. Okay. Wrong, actually. 27, because it's cubed, not squared. Apologies for that. So 3 times 3 times 3 is 27, and that all equals the mass of B. Okay. Alright, so we've got quantities in terms of the mass of A and mass of B, and hopefully you can sort of see here that we're just going to end up cancelling a lot of common factors here. So I'm going to write this as a ratio, because that's where first I'm going to look for the ratio, and then look for, because I could describe each of these choices as a ratio if I just divide across by MB. So if I write MA over MB, I'm going to do rho 0.75 4/3 pi r cubed, all divided by 2 times rho times 0.55 4/3 pi times 27 r cubed. And here you can see all the common factors. So we start with those r cubes, you can get rid of those, the pi you can get rid of those, the 4/3 you can get rid of that, the rhos you can get rid of that. And so that leaves us with, so just 0.75 on the top, and then 2 times 1, this would be 1.1 times 27, and if you do that correctly, this all gives you 0.025. So if I multiply both sides then by MB, 0.025, and so mass of A is 0.025 times the mass of B. So choice A is the correct answer. Tough question.